Hello, everybody. Just a quick check here whether you can hear me. If you do, just tell us in the little chat window you can see in your panel. Excellent. Very good. We're going to wait 3 more minutes and see if any more participants join us, and then we'll get straight into it. All right, so I think we've all our participants together now. So I'd like to introduce myself. My name is Relyon. I'm here with my lovely colleague, Andrea Beckman, behind the scenes. She'll be also communicating with you via that chat window that we just talked about. So if during the course of this little webinar we are doing today, you have any questions, feel free just to ask them in the chat box, and after that we'll unmute you to a Q&A session just after the presentation. We're calling you today from a very lovely crisp morning in Germany. For you, of course, it's a very different time, so I'm glad that we have an overlap there. And just to show you, we are in the south of Germany, southeast Germany, in Regensburg. And here in this map, we see highlighted our network of sales partners all around the world. And one of them, of course, a very warm welcome to them as well, represented by Ava Paridi, is from Nano Vacuum. They are representatives in Sydney, based in Sydney, and representing all the area Australia and New Zealand. And you probably received the invitation via Ava, and I'm very thankful that you're all joining us today. Just a very brief history, just to give you an understanding of our company. So we were founded in 2002 as part of the machine fabric Hausen. So we've been working in high power plasma applications since beginning 2000s. And you can see that in 2014, we were renamed to the name we have today, Relyon Plasma. And since then, we were joined by our major shareholder now, the TDK Group, in 2018. Since then, we've grown a bit. So we're 25 people here in Regensburg today. And in May 2020, we launched a new product, the piezobrush PZ3, which is based on a cold plasma technology that is exclusively produced by the TDK Group. So this is the connection there. So I'd say without further ado, you see it here, but I'll also show it to you live. This is the device that we'll be talking about. So it comes in this handy little case, and you can open it here. First thing you see is the manual. We have it in a lot of different languages now. As any technician will set that aside for now. So what you get here are different adapters for our plug-in power supply. Put these aside as well because, of course, today we are in Germany, we only need the European adapter. And what we'll do is we'll just plug this into a standard wall socket and unwind the cord. Don't forget that. And now with the device, we have at the back of it, there's a DC connector. And we'll just plug it in. Now you can see our logo lighting up. And the first thing you see is a message saying there's no module inserted. So module is what we have here. So these two white devices are what we call the modules. And what you basically do is you have one here that says this is German, we'll turn around this is English, for non-conductive materials. We'll start with this one. This is what we call a standard module. And you just face up the electronic board and push it until it clicks. All right. So now you can see that the device has detected the module. It says here standard module. And basically now we're ready to go. And what I want to show you is, of course, what does this device do? Just clean up my mess here. So if we have, say, something like this, this is a plastic that we call ABS, and it has a protective layer on it, like it's a sample I got from my lab. We pull off the protective layer, and we'll just treat one side of this sample. You can see the plasma coming out here. Basically what I did, I just pressed this button. This is the start stop button. And you can see that we have plasma ignited here. And if I just brush over the surface of this polymer, you can see that basically nothing has happened to it optically. Now if I go ahead and I take a bit of colored water, of course we have CI colored water here, and I spray this piece of material, you can see that there's clearly a difference in how the surface reacts to the liquid. On the side that I have treated, you can see that we have a closed film of water, whereas on the other side, the droplets bead together, you have little water droplets. And this effect, of course, this is more qualitative test here with our spray, but this can also be quantified. And for quantifying it, we look at the angle of the droplets. So I'll ask Andrea to go back to the slides to give you a schematic to help you see what I mean there. So on an untreated surface, we have these round droplets. So this is very typical for any kind of plastic material. If you've ever come across them, you know that they tend to be very hydrophobic. And this is what we call a state of low surface energy. This means that, as you just saw here, we have insufficient wetting, so there's the beading of the droplets, and this typically leads to weak bonding. With the treatment that I've just showed you with the piezo brush, with the plasma, what we basically do here is we elevate the surface energy. So we have higher surface energy, a state of higher surface energy after the treatment. This means that we have the increased wetting that you just saw, and this usually means stronger bonding. We have a lot of applications, of course, where this is very important. The first one that I want to show you is printing, because in printing, not only the bonding is important, but also how my droplets wet the surface. So you can clearly see here, for example, if you have a very hydrophobic surface, the ink droplets will bead together and you will see these little pixels in your print image. And your print image will improve the more wettable the surface gets. And to see whether this also has an effect on bonding, I'll show you a little video where I've also treated just 1/2 of the sample, and the sample we've chosen here is a very difficult material. It's PTFE, so Teflon, and we'll see how it goes. So this little video shows you an inkjet printing process. You can see on the left-hand side we have an untreated area, and on the right-hand side we have treated it with the little piezo brush, as you just saw with the ABS sample. Now, if we do a test with tape, you can clearly see that the adhesion of the tape, of the ink on the PTFE, has improved significantly after the plasma treatment, whereas the untreated side, you can see here again with the rub test, comes off quite easily and has a much better adhesive property on the side that we've treated before. So why is that the case? We have another schematic for you that kind of gives you an idea. So you can imagine that your liquid, be it the ink or be it any kind of adhesive, has bonds available. But if the surface doesn't have any corresponding bonds, you have, again, this weak bonding situation. And what we do with the plasma is we generate these bonds and make them available for a strong bonding that you can see on the right-hand side depicted with these little anchors. So you can imagine that we're kind of generating anchor groups. Chemically speaking, these probably are a lot of oxygen and nitrogen-based groups that lead to polar functionalization of the surface. And I have another little example here with me today. This is a material that some of you might also know. This is polyethylene. This is also tricky material. And what I'm going to do today is I'm going to use a pressure-sensitive tape to show you these effects of not only wetting, but also improved bonding by means of a plasma treatment. So again, I'm going to go ahead and take my piezo brush. Just press the start and stop button. You have the plasma igniting here. And I'm going to treat, again, just 1/2 of this sample. And here again, everybody has their own style. You can see that the stopwatch is running. So when I press off, I can see the time that I've treated this sample, for example. And if I'm doing a DOE, I can see what the best process parameters are. And we're going to get into what else is in store in our little display later on. For the application now, I'll peel off the protective layer of this pressure-sensitive tape. And I'll tape it to my polyethylene. And what I'm going to do now is I'm going to start on the side that I haven't treated. So what you'll see is what you've probably experienced before, where it just comes off like this. And we can see now that here in the middle, where I've started treating, it gets harder and harder for me, and eventually the tape kind of fails in itself. You can see here that the foam that the tape is made of is broken. And I can also start from the other side where I've treated, will have the same effect. So this is the difference between what we call an adhesive failure and a cohesive failure. So adhesive meaning we're failing at the interface between the adhesive and our substrate, and cohesive meaning the substrate is failing in itself because the interface is stronger than the material. And that's actually what we want to see always in bonding. Okay, I'm going to do another little experiment here with you. In the beginning, I showed you the module that I inserted, and I said this is for non-conductive material. So why is that? I'm going to go ahead and just ignore what I said before, and I'm going to take a stainless steel sample. and I'm going to try and treat it, don't do this at home, with the standard module. I'm going to go and I'm going to be here. And now you can clearly hear that the device is telling me I did something wrong. And the reason for that is that the way we generate the plasma is through very high electric fields, and we'll come to that in a sec. But basically what I want to show you is you basically change the module, just press these two buttons on the side, take out this module, and we'll go ahead and take another module out of the box, which says for conductive material. So this is what we call the near field module. And we're gonna, again, just slide it into the clips. And now I can treat this sample in a very homogeneous way. Coming fairly close to the surface. And again, I can turn it off and see the treatment time. And now you might say, okay, this is not plastic, so there might not be any functionalization, but you will still see that we have improved wettability on this sample, even more so maybe than with the plastic. You can really see that these droplets bead together, and on the other side we have this closed film of the colored water that I've been using. So why is that? Again, we have a schematic prepared for you. Clean this up. So what happens here is typically metals and other kind of not polymer-based materials, they already have bonds, but those bonds can be kind of obstructed by what we call a layer of contaminants. And these contaminants can be basically anything, but the typical contaminants are coolants, lubricants, and also release agents. And these are just typical materials that build up during the production process. So, for example, for injection molded parts, again, we're here at this plastic, they have release agents, of course, to get them out of the mold, and they will stay on the surface. So all of these contaminants are organic. So they are based on an organic compound, and by using the cold plasma from the piezobrush with the very high oxygen levels in the plasma, we can oxidize these parts and remove them from the surface if they are sufficiently thin. So we're talking about only a couple of monolayers, but these are the most important monolayers really, because for bonding, only the uppermost layers of the surface, we're talking about 10 layers or something, are really important for bonding. So if you imagine, for example, a fingerprint on the surface, these are thousands of monolayers that we have here on grease on the surface. So it's really important for any kind of bonding process to have a clean surface. And that makes available the bonding sites, as you've seen here, on the stainless steel. So basically what you do with plasma is you have a combined effect of fine cleaning and an activation of the surface. We're going to do a short recap just to give you the full overview of what we just discussed. So we were talking about wettability as a crucial indicator for the quality of an adhesive follow-up process. We saw the printing, the inkjet printing, and also the adhesive tape. We were talking about surface energy, which can be determined via the contact angle or testings. I don't know if you've come across them. Let us know in the chat window if you do. We talked just about these contaminations that we can remove with the plasma because they decrease the adhesion and should be kind of limited, and fine cleaning with plasma is one of the steps that can be at the very end of the line of the cleaning process. And we learned that plastics show low surface energy even if they are clean, as you saw with the sample at the very beginning where I have the protective layer, so this is a very clean sample, and with the plasma, even if there are no anchor groups to bond with, we can generate those. So overall, cold plasma is possible. It's possible to increase the wettability of surfaces to optimize adhesive processes. And these can be gluing, printing, coating, varnishing, potting, etc. And we'll look at a couple of use cases now after I've introduced the device in itself. So moving on to what is this plasma brush device, just to give you an understanding. So basically, we start at the end that is most important. We have an exchangeable module with a piezo element. And we'll get into that. You saw the module release buttons that I used, so the start stop button. There's menu buttons for that kind of control what we see on our display, and also enable us to move through the menu and choose different process modes. We don't need any external gas for this device. So with typical plasma systems, I don't know if you've ever experienced them. Sometimes you need noble gases. In this case, we're using just the ambient air as a plasma gas, and this is supplied by the fan at the back, where we also have the air inlet for the fan, and of course the DC power socket for the plug-in power supply. And the power we're using for this device is only 18 watts. So how can this plasma be so effective? The reason for that lies in the heart of the module. And the heart of the module is the piezoelectric transformer, which is called Seraplas and is produced by the company TDK. And what it does is basically you come in with a low input voltage of only 12 volts. And within the device, and it's about 7 centimeters long, it is transformed to up to 15 kilovolts. And as soon as that is, you have these high fields at the very tip of the device. I'll show you what happens. We'll move on to the next slide. The device, so the piezoelectric transformer transforms the mechanical movement into electrical energy. So this is the piezoelectric effect. And this means that at the very tip, when we have the high fields, at the corners of this piezoelectric transformer, we generate a discharge into the open air, which is basically the source of our plasma. And the reason that we can work at these low power levels is that there's no temperature loss, or hardly any. So the interesting thing about this technology is that there is no real risk of over-treating a plastic material through temperature, because the temperature almost always stays below 50 degrees Celsius. So you're basically always working at room temperature. Moving on, I'll show you the difference between these two modules. And now it becomes clear that if you have these high electric fields just going out into the open air, if anything conductive is in its way, there will be uncontrolled discharge. And that's not something that we want, because it makes the treatment not homogeneous. That's why we've developed this module we call near field, where we have a dielectric barrier in between the piezoelectric transformer and your conductive material. And this is how we split up our two groups of materials to treat. So on the left-hand side, you see with the module standard, we work on plastic, as you saw with the ABS, PTFE, PE, but also glass, ceramics, paper, natural fibers. And if we move on to metals like stainless steel or aluminium or any kind of alloy, we move on to the near field module. This also accounts for carbon fibers, of course, or semiconductors, or in some cases also wood if the humidity in the wood is so high that it becomes conductive. But the good thing is that this device will tell you if you're doing something wrong. Okay, we'll do another experiment for that. So I'll show you that next slide. As I have the near field module inserted here, I'm going to tell you a bit about how it works specifically. So it is based on a so-called dielectric barrier discharge. So we have to come fairly close to our surface. I'll show you this with another little sample. If I start the treatment and I'm too far away, oops, where will I go there? If I'm too far away and there is no discharge of plasma on the surface, after a while, the device will know that this is wrong. It shows you here that there you go. It shows you that this is a plasma failure because you weren't really treating the material. So in order to have proper treatment, all of these little boxes have to be green. And for that, now you can see it's yellow, plasma is yellow. So we're working in an area where we're not treating effectively. But when I come close, we have an ideal treatment, and the device will detect that and keep on going. This doesn't only work on the material, on the conductive material itself, but also if there is another dielectric layer. So say if we have a glass sample, so these are little glass samples, and I put this on top of my conductive layer, I can have a very effective treatment of the glass because I'm really focusing the plasma treatment in the gap between my near field module and the uppermost surface, in this case, the glass layer. And we'll also check this for wettability. So if I spray this, you can clearly see that we have achieved sufficient wettability in the area, the middle where I have treated this glass sample. Okay, this is what I always like to call a sandwich treatment, which can be very interesting, but which is also important. If I typically ask somebody on the phone, what kind of material are you treating? And they say polypropylene, and it turns out that their polypropylene is actually just a very thin layer on top of the metal housing. In this case, the near field module will be the right choice. Okay, we'll go back to that slide just to give you a short recap. So basically, if distance is too high, there's no plasma, the device will tell you after a while if it detects there is no treatment. The proper treatment is if you come close enough, and display shows you that you're in the proper range. And there's also the possibility of using a thin insulating layer on top of a conductive substrate and have this kind of sandwich treatment. Okay. So speaking about the display, we saw that it kind of uses the purpose, it has the purpose of letting you know what's going on. So at the very top, it shows you what kind of module is inserted. So currently we have the standard and the near field module. Towards the end of the year, we're planning for other modules to be developed. Specifically, we're looking into modules that have a more defined plasma, like needle modules, or modules that can use also different gases to be injected, as we have in the previous model, the piezobrush PZ2. We have a multi-gas nozzle, as we call it. This will be also be transferred onto the modules of the piezobrush PZ3. But with PZ3, we also have process tool modes. So you saw the stopwatch, but there's others. And I hope you'll be able to see this on my display if we move. So now, so basically, turn like this. You can see this is stopwatch, but there's also, I think this is countdown. And here we have metronome. So with countdown, I can set a time. Say if I saw in my DOE that I need 15 seconds typically for an area of what you have, you can set these 15 seconds on the timer. I'll set 5 seconds so you can see what happens. So with 5 seconds, and I'm going to again use my little sample here. I'm going to start the treatment. And after 5 seconds, it's going to just stop. So this enables you to have like a series of experiments that always have the same timing on each sample. Same accounts or similar accounts for the metronome mode. Here you can set a time, and I'm going to show you that as well. So also 5 seconds, and it's not going to stop, but it's going to give you an acoustic indication of that your treatment time has elapsed, and you also have a visual bar moving on if you see your treatment time elapsing. What else can be accessed through the display? There's a power setting. So I always work on 100%, of course, but you could also move down, I think as far as, oh yeah, as far as 40%. So this can be interesting. We saw that it's still a fairly effective treatment, but for example, you have less ozone emissions. Ozone is something that is generated via the cold plasma. Here in the, you can't see, of course, but this is a well-ventilated room. It shouldn't be any problem here. But if you have colleagues, as I have, that are sometimes a bit sensitive towards the ozone smell, you can also use like a solar extraction unit to kind of suck away these emissions. Buzzer volume, so to have kind of, you can mute this device if you mind the beeping, and we can also change the orientation of the display. So now we're in landscape mode. Okay. And then you have info basically in the box here. Yeah. So we're going to move back to the slides, because I wanted to show you it's not always easy to see with the camera these 3 boxes I was talking about. So we have plasma, fan, and temperature. And if any of them are critical, as we saw with the plasma, in case of not being close enough to the metal substrate with the near field module, it will show you critical for a while, and then it'll go to error. And error will also show up if you're treating a conductive material with the near field, with the standard module instead of the near field. Okay, moving on to the next slide. Which gives you just an overview of the scope of delivery, basically the case you saw me open in the beginning. What's not included in this picture is the manual, but you know it's in there, and the country adapters. So we have this plug-in power supply can be used all over the world, and we have the different adapters in it. And you can see that we have the 2 modules that we have developed, they're in there, and as soon as we develop others, they can be included and just be used similar. Okay. So the electrical connection, you can see it can be used all over the world. We have the 18-watt power consumption. It's of course a handheld unit with plug-in power supply and integrated fan. Plasma temperature, we're talking about that. So below 50 degrees Celsius. Very lightweight, and treatment speeds, just to give you kind of a rough idea, will be 5 square centimeters per second. We've seen faster treatments. Some materials need a bit of a slower treatment. Some materials, like very thin films of polymers, they need actually the toning down of the power as well that you saw when we go down to 40%, because the discharge can be damaging to very thin films. So this is another great development, I think, from our colleagues and from our engineers, that they said we're going to tune down the power that will make it possible in this device as well. Treatment distance 2 to 10 millimeters. So as I said, with the near field, come close to your surface. And the width is around 20 millimeters typically, and we'll be moving on to a bit wider and smaller modules during the course of this year. Okay. So talking about materials, of course, you saw that we are in plasma business for some time, and there have, of course, been two predecessors, piezobrush PZ1 and piezobrush PZ2. This is something we did with the customers of our PZ2, asking them what kind of materials they are treating, and you see the overwhelming majority here is brushed plastics. But there's also a couple of metals here, aluminium, stainless steel, silver alloys, copper alloys. There's stone, there's glass, there's ceramics, and other metals. Silicon is also in there. So we're going to focus on the plastics a bit more. And here you can see really a very wide variety of materials. Polyamides, we'll be talking about a use case in 3D printing in just a sec. Polypropylene, polyethylene is in there, PEEK, polycarbonate, and you can see that the list goes on and on. The question being, what kind of processes are these materials being used after they've been activated with plasma? And this will be shown on the next slide. So the majority of our customers say they improve adhesion and gluing. There's also cleaning, printing, varnishing. So these are the typical applications. And we'll move on to some use cases to give you an idea of the real way this device is being used. So this is one of my favorite examples. We're looking at PA12 printed parts. They're SLS printed. This is a customer of ours near Munich, and what they do is they print prototypes for the automotive industry. Of course, typically these prototypes are bigger than their printers. So what they have to do is they have to join the individual parts, and they use the piezo brush on basically all of these parts because they have seen that they can increase the bond to be 3 times stronger after this piezo brush treatment than just basically spotting them and gluing them together. So what they do is they spot them, so they activate them, they spot them with super glue, and then after an hour or so, they go over it with a 2-component adhesive. And after an hour, the activation is still active, so they have a very strong structural bond that they can achieve with the piezo brush. Another lovely application that we have here is something that is more towards the analytics. We wanted to find out together with a company that manufactures and distributes these devices that show you how thin or how thick a contamination layer can be on a surface. In this case, again, we work on stainless steel, and what they've done is they have a contamination, a defined contamination layer, and when moving over the surface with the near field module, you can see here that at a speed of 2.5 millimeters per second, clearly you are cleaning this film off the stainless steel. So this is really a fine cleaning process. And what happens to it in an application can be seen in something that I didn't expect, and this is wire bonding. So this was done together with a company called TPT, which is a joint partner of ours and Nano vacuum. And what they looked into was when they do a heavy wire bonding of the surfaces, the contact surfaces of batteries, they see a strong increase of the pull force and the shear force average of these bonds after plasma treatment. So not only can we theoretically show that we do fine cleaning on metals, but it also shows in the effects of a process like wire bonding, preventing these so-called lifts and non-stick on pad. Very interesting market that we've grown more and more into is the medical market. So here we come across very difficult materials all the time. So fluorine-based polymers like PTFE or FEP, which can be very tricky for bonding. The alternative to plasma activation is oftentimes very aggressive chemicals to be used. And here we've also seen high improvement rates of the bonding of, say, tubing, for example, by using the piezobrush. Another application that is also very common in microfluidic chip manufacturing is bonding of PDMS on glass. And here, normally people use big plasma chambers that are fairly costly and oftentimes not as easily accessible. And here we saw that also a lot of universities, a lot of institutes go to the piezobrush because basically the process is as easy as pie. Another application is in what you see on the right-hand side here is increasing the wettability of implants. So this is something that might also be interesting for you, but also in the broader vicinity of the dental market, for example, working on veneers, working on kind of all these intricate little parts that are part of the dental technician's job. Here we are also very successful with this cold plasma technology. Again, going back to academics a bit, but staying in medical field. So this is an investigation on a material that some of you might know. This is PEEK, polyether ether ketone, which is oftentimes used in medical because it has very specific properties. But what it doesn't have as much is properties of bonding. And you can see here that we had them examined, these PEEK substrates. There's a reference sample where we've measured the surface energy. You can see that the surface energy splits up in a polar and a dispersed part. After sanding, so this is of course also a process that can be used for increasing bonding, you can see that we have increased the polar part. This is low pressure plasma that you see here in the middle. We also see an increase in polar, and we do the same with the PVD plasma, which is the technology that we use in our piezobrush. The interesting thing is that if you look at lab shear strengths of these samples, we can actually absolutely compete with the low pressure plasma. So this is something that I was quite intrigued with. And what also came out of this investigation was some lovely pictures from the AFM, which show you that what we also do on the surface is a kind of nano roughening. So it's not only the generation of these anchor groups that are basically just chemical groups, but also a roughening of the surface that leads again to increased bonding. Okay, just to have a quick recap at the end of my little presentation here. I hope you've all enjoyed it. So today I introduced to you a highly efficient cold plasma for optimizing adhesive processes. I hope you took away, were inspired by some of our use cases, and we would of course be very interesting to hear about your use cases or your ideas. The materials are always important, of course. Which materials do you work on, be it plastic, be it metal, be it glass, ceramic, semiconductors, natural materials? As I said, we divide them into groups, conductive and non-conductive, and there's also the kind of in-between sandwich treatment that we talked about. You saw applying the plasma is easy, safe, and intuitive. We have these process control tools, power settings, and these can also be accessed via the integrated display. There's no external gas required, so we use just the ambient air via the integrated fan, and it's just plug and play. just plug it in and you're ready to go. And now I think we'll move on to Q&A. I'm very excited to hear about your feedback. So now you're allowed to unmute yourself and bombard me with questions. Or of course, you're also very welcome to write your questions into the chat window, and Andrea will read them out for me and I'll answer them that way.
So one question is an overtreatment of the surface possible?
Yes, it is, but we're not. So we have to differentiate between thermal overtreatment. So we also here in Regensburg, we also have a high power system where we oftentimes see overtreatment thermally. This is not possible with the piezo brush. However, we're working with very active gas molecules, not only the ozone, but others that are much more active. So if we are in our durability tests, we can see that there's really etching on the plastics, but this is on a time scale that is far beyond what you will actually see with a handheld device. So this is really going over nights and over days. You will see that the materials will be affected, and therefore we use very durable materials for our nozzles, of course, for our modules.
And how high is the temperature of the plasma?
So the temperature we specify with being below 50 degrees Celsius. You can experience, especially near field nozzle, becoming warm if you have a longer treatment on the same spot of a metal. So there, I'd say you might be in the vicinity of 50 degrees Celsius, but if you work on plastic with the standard module, you basically stay at room temperature. Oh, this fellow's falling.
And is it possible to integrate or automate this device?
Mm-hmm. Excellent question. So because these handheld devices are absolutely as a USP for us, we started with the redesign of the handheld first, and this is the result. I think well done to our colleagues there. And there is another device that you can also find on our website, and also with Nano Vacuum, is what we call the piezobrush PZ3, which will be also redesigned, probably very similar with this modular design. And these devices can be integrated into the line. They no longer use the ambient air, but they can also be equipped with external gas inlets, and then of course external in and output signals. And since we're still in development of these devices, we'd be very interested to hear from you what kind of interfaces you use for your current plasma treatment maybe. So are you using bus systems or just analog signals? If you have any input on that, just let us know.
And is it safe on human skin?
Excellent question. We'll do this experiment here. So I'm gonna come close to my finger. So basically, this is the treatment that is not very pleasant. So if it happens to you, don't be scared. You don't have to go to the hospital. But this device is not specified as a medical device. We're currently working on our medical certification, but currently, as I said, this is a device that is meant for surface activation of materials and not to be used on humans or animals. But it's safe to touch the plasma discharge. It's not recommended. And yeah, so currently this is only for non-medical use.
Can a metal surface treatment change the surface charge of the substrate?
Yes. This is an effect that you might know from corona discharge systems, a kind of bombardment of ions. We've seen very interesting effects not only on metals but also on semiconductors. For them, of course, these things are very critical. And here you can experiment, for example, with a grounded cylinder. For example, we saw that if we have discharge on, if we have the plasma on a semiconductor, and between the semiconductor and our plasma, there's a grounded cylinder, we can eliminate some of the charges, but we can't really adjust it for being like an anti-static device. But we're very interested, of course, in knowing whether your application would be suitable for our device. But definitely there's charge involved, and it can be adjusted, kind of a solution that you have to figure out a bit yourself, but we'll be definitely bringing that back into development as well.
So, and what's about the price of this device? Is rental possible or collaborative projects?
I think that's a question I'd like to give back to Ava from Nano Vacuum. So currently here in Germany, we would be around, I think, 2,500 euro roughly, just to give you an idea here in Germany. But of course, our experience is the most important thing is really the rentals and the trials, which we can't supply outside of Germany. So therefore, we have our sales partners that can supply you with rental devices and also with their experience and expertise.
And is it possible to upgrade the device if there is an update in the future or if there are more modules in the future?
Yeah, absolutely. So all coming modules will be compatible to the device. And of course, as you've probably seen, we have these contact boards. So they are capable, if we put a different software on them, on the EEPROM, we're able to also access different layers of the software on the device. So definitely we're looking towards an upward compatibility here.
I think that's it for the moment.
Cool. So thank you so much.
Sorry, I just wanted to thank you for such a great webinar.
Oh, thank you.
It was amazing.
Thank you so much. No, it was an absolute pleasure, and thank you all for staying in late, I suppose. I have really no idea of time at the moment because we kind of came here at 6 a.m. in the morning, and it's a weird idea talking to you at the end of your day.
No, it's 4 p.m. here in Melbourne.
Yeah, no, thank you so much, and everyone for joining. If another question comes to you, please feel free to either send it to Ava or us, and that same accounts for feedback, of course. If we'll talk about modules and further development of the device and also integration of the device. If there's anything you want to share here, just let us know, and do join us on our social media channels. So Andrea is very active on LinkedIn, as is Ava and James. So please, we'll always be up to date if you'll follow us there. And there'll be videos and use cases and customer references, which I think is always very interesting to kind of give you also an idea what really large variety of applications this device is used in. Excellent.
Another question?
There you go, yes.
Is there a partner in Romania for this device?
I think there is, yeah. I think it's the Albrecht Group, yeah. For that, do check out our website, hit the button International, and you will come to the map I showed you in the beginning, and this is an interactive map. And you can hit the country that you're interested in, and you'll be redirected straight to your sales partner. And they are, of course, always in close touch with us. So we're very much looking forward to you getting in touch with them. Cool. Excellent. So thanks again to everybody. Stay safe out there. Follow us on social media. Let us know if you have any other input or feedback. And yeah, looking forward to hearing from you next time. Goodbye.
Das ist so geil. Irgendwann kann man immer keine Fragen, die ersten 3 waren von mir.
Mhm.
Und dann geht's irgendwann.
Ausgezeichnet. Vielen Dank.
Ja, vielen Dank.
Und ich hoffe, ich habe keine Ahnung, was ich habe. Habe ich das so Sinn gemacht?